Pluto is a distant and puzzling planet that was once fundamental to our nearby planetary frameworks family. However, disturbing statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a frightening revelation. They suggest that it is on a potential trajectory to collide with Neptune. Yet, how could this happen, and what might be the outcomes of such an immense event? Are we witnessing an impending crash? Or is there something else about this oncoming cosmic disaster? Join us as we explore the possibilities of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet partly due to its unusual orbit, remains a subject of fascination and study in the scientific community. According to recent estimates by leading experts, Pluto's orbit is alarmingly close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising concerns about a potential collision between these two celestial bodies that could have significant implications for Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its uniquely warped shape, deviating drastically from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is far more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to decipher its peculiar trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stands out with its steep inclination and irregular shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The intricacy of Pluto's orbit amidst these complexities is a testament to the complexities of space mechanics. The three-body problem in space is about determining how three objects, such as Pluto, Neptune, and the Sun, move and influence one another with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto, this problem reveals how its orbit, Neptune's path, and the Sun's gravity all interact in a convoluted way. The terms alpha libration and degree libration, along with the VZK effect, are critical to this question. As explained by astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. Regarding Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is positioned roughly 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an additional layer of protection from potential collisions. Another significant factor in this situation is the VZK effect, named after three scientists Zippel, Leo, and Kai who studied how objects move in space. It describes how three celestial objects, like Pluto, Neptune, and the Sun, influence one another with their gravity. This pull affects their movements. In Pluto's case, the VZK effect helps us understand why its orbit around the Sun is so unusual. Despite appearing chaotic, this interaction helps keep Pluto moving smoothly. The VZK effect demonstrates that while space may seem wild and unpredictable, certain patterns and rules maintain control. These factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or lose its path. This three-body problem is key to understanding how orbits evolve based on the gravitational interactions of celestial bodies. Focusing on this helps us learn more about Pluto, our solar system, and even distant stars and galaxies. Numerical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit is still somewhat chaotic, with minor variations in initial conditions leading to significant differences over long periods. However, these remarkable properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a unique relationship with Pluto, where, for every orbit Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only player in this. Jupiter's gravity also plays a critical role in protecting Pluto's orbit, and Saturn contributes as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady path for millions, even billions of years. It appears that Neptune, Jupiter, and Saturn work together to ensure Pluto continues moving safely through space without encountering problems. These phenomena are crucial in understanding the universe, as they maintain the control and consistency of celestial bodies' movements. Without these forces, the solar system as we know it would be a place of far greater chaos and unpredictability. Bodies like Pluto might collide with others or be ejected from their stable orbits, causing a domino effect on other celestial bodies. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is essential. This provides a clearer picture of the dynamics of our solar system. The case of Pluto shows how even the most seemingly unstable orbits can achieve a state of stability through the intricate interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or velocity can significantly alter its long-term trajectory. In the vastness of our solar system, Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant discoveries about its structure and behavior. One of the most captivating aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and various compounds. NASA's New Horizons mission, which flew by Pluto in July 2015, provided groundbreaking data about this distant world. The surface of Pluto is characterized by vast plains, towering mountains, and deep valleys. One of the most surprising features is Sputnik Planitia, a giant heart-shaped plain made primarily of nitrogen ice. This area showcases a variety of landforms, including massive ice shelves and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active, despite its vast distance from the Sun and frigid temperatures. Another fascinating aspect of Pluto is its atmosphere, which is primarily composed of nitrogen with traces of methane and carbon monoxide. While Pluto's atmosphere is thin, it exhibits intriguing seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex interaction between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze onto the surface. Conversely, as Pluto moves farther away, these frozen gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, adds another layer of complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies share a mutual orbit around a point in space that lies between them, rather than Pluto simply orbiting around Charon. This unique relationship contributes to the intricate gravitational dynamics in the region, influencing the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to various other dwarf planets and potential impactors. This belt serves as a reservoir of ancient material from the early solar system, providing scientists with insights into its formation. Pluto's orbital characteristics may offer clues about the evolutionary patterns of these distant objects, suggesting that interactions with larger planets could have played a critical role in shaping their current orbits. Understanding Pluto's orbital dynamics also has broader implications for comprehending the development of the solar system. Gravitational interactions with neighboring giant planets like Jupiter and Neptune can alter the orbits of smaller bodies, including those in the Kuiper belt. Such interactions can lead to orbital changes, potentially resulting in collisions or ejections from the solar system. As researchers continue to study the details of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to reclassify Pluto as a dwarf planet in 2006 was controversial, sparking debates about the nature of planets. Pluto's orbital relationship with Neptune and its position in the solar system serve as powerful reminders of the complexity of the universe. Through continued investigation, we can deepen our understanding of these distant worlds and the forces that govern their motion. As we continue to explore Pluto's unique orbital dynamics, it is essential to recognize how the gravitational forces exerted by distant planets shape the behavior of objects in the outer solar system. While Pluto's orbit may appear chaotic at first glance, it is precisely these intricate interactions that allow it to maintain stability despite its apparent unpredictability. Delving deeper into the mechanics of Pluto's orbit reveals additional layers of complexity, shedding light on the dynamic processes that govern the motion of celestial bodies. One captivating aspect of Pluto's relationship with Neptune is the long-term stability of their orbits, despite their occasional proximity. This is due to a unique resonance between the two bodies, known as a 3:2 orbital resonance. For every 3 orbits Pluto completes around the Sun, Neptune completes 2. This resonance keeps Pluto and Neptune in a stable configuration, preventing them from colliding despite their orbits crossing. The stability provided by this resonance is a remarkable example of how gravitational interactions can ensure the orderly movement of celestial objects. This 3:2 resonance results from the gravitational interplay between Pluto and Neptune. Each time Pluto and Neptune approach one another in their orbits, their gravitational fields interact in a way that keeps their paths synchronized over long periods. The outcome is a system where, even as Pluto crosses into Neptune's orbit, the two bodies remain carefully spaced apart. Thus, the likelihood of a collision is virtually non-existent.